Hi, and welcome to the Biomechanics 1 video series. This particular video is looking at concepts around the center of mass. So, in many instances, when I have a fairly uniform body, so let's say, for example, this was a rectangular ruler, the tendency would be to say that the center of mass is most likely located somewhere in the middle, which conceptually might be difficult at first, since we know, say that, for example, or for argument's sake, that the mass of this ruler is about 1 kilogram. It's a fairly heavy ruler. Why would all of its mass essentially be centered in the middle, and how do we even know that it is centered in the middle? Well, one simple way to do that is normally if you kind of think about placing a finger, and this is a pretty arbitrarily drawn hand, but let's say, for example, you had to place a finger and you were trying to find a way to balance this particular ruler. So if you were to place your finger directly over the center of mass, essentially what would happen is you'd have a balancing of the forces. In other words, the mass of the ruler would be pointed downwards and the force of your finger would be pointed upwards, and if these are equal and opposite, then you would have a static equilibrium scenario. If, however, you were placing your fingers slightly to the left of that center of mass, essentially what would happen is you'd have this sort of clockwise rotation, or alternatively, if you had to place it to the right, you would have this anti-clockwise rotation that would happen. But if you get it perfect and in alignment with that center of mass, you would have a balanced or like static equilibrium situation. Now, for uniform objects like this ruler, or if you had something like a square, or if you had something like a rectangle or a sphere, typically what tends to happen is that the center of mass is at the geometric center of all of these objects, and it is fairly straightforward to calculate these even mathematically. But where it really becomes interesting is when you have odd-shaped objects. So say, for example, you had something like a baseball bat, where the mass distribution is not even. In other words, there tends to be more mass towards the heavier end and less mass towards the lighter end. Where would this center of mass be? Or if you have multi-segmental bodies, so for example, the human body, which has varying mass distributions, and it is made up of several objects, so essentially limbs in this case, how would you go about determining where the center of mass of that is, and why is that even of any interest? So what you would realize is that if I were to throw, let's say, this ruler object, each point on this object would follow quite a complicated path, which would be very difficult to interpret and to essentially predict where that motion is going to be. But if you had to throw this ruler and you trace the center of mass of that ruler, all of a sudden the complexity of its path becomes much more straightforward. As you guys would have learned from projectile motion, essentially if I throw and I launch this ruler, then its center of mass would follow this sort of parabolic path, and all of a sudden that becomes much easier to interpret, and it becomes much easier to predict what that motion will tend to be. So there are ways to calculate where the center of mass is going to be, especially for a multi-particle system. So if I kind of just get rid of this for now, and let's say I have this multi-particle system. Let's say, for example, I have this sphere of 3 kilograms and a bigger sphere of 10 kilograms connected by this essentially massless rod. I'm just going to leave the mass out for this to make calculations and interpretations of this a little bit easier. Intuitively, if I were to try and balance this, let's just say it was like a really odd shaped like dumbbell. Oops, sorry. If I had to try and balance this on a finger, which obviously I couldn't do because it's just too heavy, but if I had to place this finger somewhere, now all of a sudden I wouldn't put it in its sort of geometric center, if you want to put it that way. That wouldn't really work. The intuition would be to place it somewhere towards the heavier end, right, in order to try and get it to balance. Essentially, like, you could think of this as a simple lever system where the finger is the fulcrum, and these would be masses on either end of that fulcrum. How do I make sure that I can balance this out? And you would, from those lectures, remember that the heavier mass has to be closer to the fulcrum than the lighter mass, or the lighter mass can be further away from the fulcrum in order to balance a heavier mass. The question is exactly where do I have to place that finger or that fulcrum in order to balance the situation. And what's really interesting is that that can be modeled mathematically quite easily in this type of a setup. The only thing that you have to do is to draw an arbitrary axis. In this case, I'll draw a y-axis, and then the only thing that I have to know is what the distance of each of these masses is from this y-axis. And in this case, I do know. In this particular setup, this first mass, this 3 kilogram mass, is a distance of 2 meters from my x-axis, from my y-axis, and the bigger mass is a distance of 8 meters from this y-axis. Now obviously if I draw this axis further out, then these distances would change, and I'd have to again know what those distances are. So if I drew it 2 meters further out here, the distance of mass 1 would be 4 meters, and the distance of the second mass would be about 8 meters, right? Sorry, 10 meters. So you'd have to account for those differences. So as long as you know what the distance is from this axis to where the masses are, then this equation will work. So we would know that there's a horizontal distance involved, which we'll call x. So there's an x component to all of this. And the question is, where should the center of mass of this object be? In other words, where should I place that hand or that fulcrum relative to this axis in order to balance the system? So the equation looks something like this. Essentially, it's the sum of all the x components, where there might be, in this case, a number of objects from 1 to however many there are. In this scenario here, it's only 2, multiplied by the masses of these individual components. Right, so since each of these is a certain distance, a certain x distance from the axis, and it has a certain mass, this is what we're accounting for. I'm going to show you guys now how to use it. Divided by the sum of all the individual masses in the system, and again, that can be arbitrarily large. In this case, it's from 1 to n being any number of particles. There can be more than one, there could be 100, there could be 1,000, doesn't really matter. If I know the masses of each of these, I would add all of those up. So luckily in this case we're only dealing with a 2-particle system. So how do I go about doing that? Now it's just a case of plugging it in. The x1 distance is what I plug in here, multiplied by the mass of that first object, plus the x2 distance multiplied by the mass of that second object, divided by mass 1 plus mass 2. So you would get the gist for how this would work. If there were n particles in the system, I would need to know the distance of that particle and the mass of that particle, right? And then that would just be divided by the addition of all those masses. Okay, but we don't need to do it since we only have 2, so I'm just going to keep it at that, and then just plug values in. So x1 distance is 2 meters multiplied by the mass of that particle, which is 3 kilograms, plus the distance of that second particle, which was 8 meters, multiplied by its mass, which was 10 kilograms, and then I divide that by the sum of all the masses, which was 3 kilograms plus 10 kilograms. Alright, so that leaves us with a total of 86 kilogram meters at the top, divided by 13 kilograms at the bottom, and that gives me a total value of about 6.62 meters. Notice the units are definitely going to be meters. The question was, where essentially do you have to place that fulcrum in order to balance this out? So what you'll notice is that since this is 2 meters and the second one is 8 meters, if I were to place essentially a fulcrum directly in the middle, I would be placing it at about 5 meters, right? 5 meters is sort of the geometric center between these two relative to this particular axis. But what you'll notice is that I actually need to place my finger at, or the fulcrum at 6.62, which is a little bit more skewed towards the heavy side. So in other words, this particular fulcrum, this particular fulcrum I would need to place closer towards the heavier mass excuse me, in order to balance the system, or essentially that is where the center of mass of this two particle system is located. Right? So now all of a sudden, if I had to say throw this particular object, so if I just plug that in there again, and it were to follow some kind of path, the individual motion of these two particles would follow again quite a complicated path. But if I had to trace where the center of mass is moving, it would again follow that same parabolic path, which is great to know, right? Because now we can make some predictions about where this object will land, if a force is applied, what its acceleration will be, so on and so forth. And something that is essentially complicated becomes a lot more simple and much easier to deal with. Okay, so this is simple one-dimensional stuff. But obviously now the question would be, well, what would happen if I have a slightly different scenario? Let's say I have the exact same two masses. I'm just going to try and draw essentially to scale over here what it was above. And again, let's say they were connected by this massless rod. Now these two aren't directly in alignment. I can still draw my arbitrary axis, but now you can see that they're offset. They're not along that same horizontal line. So there's a little bit of deviation vertically. So if I again draw a horizontal axis now, where this is the x-axis and this is the y-axis as before, I can follow the exact same principle. What you will notice is that the center of mass would have shifted. It's still in alignment between these two. It would still have the same horizontal distance from the y-axis. So these two should theoretically still be aligned. The only difference is how far has it moved up. So as long as I know essentially how far this distance is over here, in other words, how much the second sphere has moved or deviated from that x-axis, in other words, it's got some vertical displacement now, I'd have to know what that is. And let's say in this case it was 4 meters. This obviously is not, it's still exactly in alignment with the x-axis and therefore has not deviated vertically at all. So the question is, what would be the y center of mass? Where would I have to place it vertically in order to still balance the system? Well, again, this is going to work exactly the same. It's the sum of all the y components multiplied by the individual masses, where it can go from 1 to many, divided by the sum of all the individual masses in the system, where again it can go from 1 to many. In this case, we still have only a 2-particle system, which makes the calculations a lot easier. So this essentially would be y1 times mass 1 plus y2 times mass 2 divided by mass 1 plus mass 2. Again, if I just plug values in, I'm just going to bring it down here. So y1, we say that this hasn't deviated at all, so that's 0 times its mass, which is still 3 kilograms, plus y2 we said was 4 meters multiplied by 10 kilograms. Again, that's just divided by the sum of all the masses, which was 3 kilograms plus 10 kilograms. And we're essentially left with 40 kilogram meters divided by 13 kilograms. And again, I'm left with a meter value, which in this case is 3.08 meters. So essentially that's saying that if this center of mass is 4 meters, again, you would expect that to be closer to the heavier mass, vertically speaking, than the lighter mass. So this distance over here is 3.08 meters. So quite easy to find any deviation of particles within a system, and they can be arbitrarily large. If you just follow the simple equation, you will always find where the center of mass is. So what I've done to kind of help with this is I've made an Excel application that can help you guys work through quite a large number of examples. So this particular one, let me just make this a little bit smaller so you guys can see what's going on. You can work through any number of particles. So there's 2-particle system, 3-particle system, and a 4-particle system. Let's say I were to rerun this exact same example that we had here. So I'm going to put the masses in. It was 3 kilograms for the first mass and 10 kilograms for the second mass. I said initially this first mass is 2 meters from the y-axis and 0 meters with vertical deviation. Then the second particle was 8 meters from the y-axis and 4 meters up. So the question is, where's the center of mass going to be? Well, the goal is for you guys to do those calculations. Once you've done your calculations, you can just click the show answer button, and it will give you the answers that we had calculated, obviously to greater precision, but you'll see here where the center of mass is then located, which is exactly what we had done in our calculations, right? You can scale that up, introduce 3 different particles. In this case, we have particles of the same mass, they're just located differently, so you can play around with it again, finding out the sum of all the x deviations and the sum of all the y deviations relative to those masses, and find out where the center of mass is. In this case, once you've calculated it, essentially it should be the geometric center between these 3 particular particles. It's not going to be pulled further or closer to any one of them particularly. It just depends on their orientations. Right, and same thing with a 4-particle system. Here we have ones with vastly different masses, some being 5 times heavier than others. They're all at the same height, so essentially this is like a horizontal rod with different mass distributions. The question is, where's the center of mass going to be? And again, you will see where that is. It's along that same horizontal line, and its distribution, or the center of mass where it's located, can be calculated quite easily. This is pretty straightforward stuff, but we can expand this to even more complicated systems where the mass distribution is not even. Something like the human body. So here, for example, let me again just make this a little bit smaller. Here, for example, we have a human that is going to perform a standing broad jump. So here's the foot, here's the shin, here's the thigh, here's the trunk, this is the upper arm, and then this is the forearm. So I have modeled in the head, because we take this from video, we've digitized it, and then we can play through. Obviously something like the trunk is going to have a lot of mass, and something like the thigh is going to have a lot of mass. How that's distributed can be found from very specific tables, which I don't have here at the moment, but they're in your textbooks. All I'm interested in showing you guys at the moment is where the center of mass is located. Essentially, in this case, it's located outside of the body. It doesn't have to be inside of the body, which I'll get to in a second. But it is essentially non-fixed. I think that's the key I'm trying to make here, is it is not a fixed position. Its orientation changes as the orientation of the body tends to change. So I'm just going to run this through to show you how, as the person swings the arms through and gets ready to launch themselves in the air, you can see that the center of mass is now within the body. And then again, as the shape of the body tends to change, it can fall outside the body again, and then the person lands. What you'll notice is that the center of mass, as the person is flying through the air, essentially follows this parabolic path. I've also included this sort of arbitrary path here, just to show you that's the path of the wrist. So you can see here that as the wrist is moving, it's following this really sort of complex path. I can also show the path of the elbow joint. I can show the path of the, elbow joint, the ankle joint, say for example down here, right? And then the path of the toe as the person tends to jump. So they follow all these complicated paths, but the essentially the sum of all of these individual parts which make up the center of mass becomes this sort of very predictable parabolic path, which we can make calculations about, predictions about. We can find out and calculate essentially how high the person has jumped, how far the person has jumped, so on and so forth. So even though this body is complicated, once we know a lot of things about it in terms of these segmental masses, we can make some really, really great calculations and some really great predictions. And essentially that's where I want to leave it for now. The key that I wanted to say is use this center of mass calculator. You can, again, like I said, put any values in here for masses and coordinates, and then see if you can calculate what the answers are. Just remember to click the show answer button and see if your answer is the same as that has been calculated by the computer. That's it for now. Thanks for listening.